The last topic I'm going to cover are velocity perturbations, and what we are going to do now is to again use the very same hydrodynamical equations, but we are going to combine them in a way not to extract the fluctuations of the density, so the density contrast, to have therefore a solution in terms of the density contrast, but we are going to combine them in a way such that in the end we obtain the peculiar velocity perturbations, so the peculiar velocities, which are the velocity perturbations in comoving coordinates u. Okay, so we solve the same set of equations, not to derive the evolution of the density, but we are going to derive the velocity perturbations, so the solutions for that. How do we do it? Numerically. Okay, there's no way out. You need to get your computer and solve those equations numerically. But that's something I cannot do on paper, therefore what we're going to do is to take some simplifications. So we're going to make very simple assumptions and actually very well physically motivated to derive an analytical solution. So let's do that. What are going to be our assumptions? One is that the velocities are aligned along the gradient of the gravitational potential, like that. Why? You can imagine to have an overdensity, so imagine a blob of material which is slightly denser with respect to the surrounding, and how the gravity is going to look like. How should be the acceleration and the velocity caused by the gravitational force of this material? Well, should point in the along the center of this overdensity, and meaning pointing at the center of the density, it means that the velocity fields must be aligned with the gradient of the gravitational potential, like that. Okay? Then what we are going to assume? Well, we are going to assume that the amplitude of this velocity scale with a certain function u of t that we need to quantify. And that's it. So you see, very simple, very clean physical motivation. An overdense region is calling material along the gradient of the gravitational potential, which is what? The force. Right. So let's do that. And what we do is just, we start with a mathematical trick, if you want, that we are just apply the operator to u, meaning we are applying this operator to this function u, like this guy here. For u of t has not any spatial derivative, and therefore is not being affected by our operator, whereas this quantity has the gravitational potential that do depend on position, and therefore the operator must be applied to that. Then what we do, we get rid of the potential, or better, we express the potential in terms of the density using the Poisson equation. So you see, we have this term that is going to be transformed into this term, just using the Poisson equation. Then what we do, we work out this other term of the equation, and we just exploit the continuity equation. Look what we have here, our beloved continuity equation. So we know that the u, which is this one, is equal to minus delta dot. And here we have it, the u equal to minus delta dot. Then we just express our delta dot as a, we just re-express this derivation in terms of derivative of the expansion factor a. So that's what we did from here to here. Then we just introduce the definition of h, which is a dot over a. So we just plug it into here, and we get this expression. So just matter of definition of h dot. So we now can substitute this term with this one here, and we obtain that. Then we continue, once we combine these two terms together, and we are going to substitute 4 pi g rho b, 4 pi g rho b, with the definition of of omega, because remember this rho 0 is the background, So I wrote 0, t should be a b. So that's our rho b for the background is just defined as omega m times rho critical. So I'm just using the definition of omega m. And I obtain this expression here. There are a few simplifications that take place. Therefore, all of these terms here, these ones, are going to be substituted by that. And they are popping up here. Then we can continue. And we just define, well, actually, then we continue then. And we are going to substitute now this side of the equation with the growth factor delta. So we just substitute the solution that we derived with the previous derivation. So that's a result that is coming from our previous derivation, and we just plug it into here. That's our final expression. Well, into here and into here. Okay, we substitute all delta, obtaining this expression. Then we just define a quantity for a label. We label this quantity for convenience as f. So we call this guy, you see this is the same function, we just call it f of omega. And here we make an approximation. With the numerical solutions, we know that this f of omega, so this quantity here, is actually very close to this expression. So it is basically as a dependency that is dominated by omega m, and there is this power that have been found through a fitting. Okay, so that's a very, very, very good approximation that is coming from the numerical evaluation. And then that's it, because this is just our f. Here we have u that we just isolate, meaning we just get all these terms here and we bring it on the other side of the equality, obtaining this expression. Okay, once we have that, we are done. We have our solution, because now we have u as a function of the scale factor. Remember that the scale factor is a function of time. Okay, and we have therefore this equation that is fully expressed. So we know everything about the velocity dispersion, because we know how the amplitude of the velocity dispersion, the proper velocities, are evolving as a function of time, and we just have to multiply by the gradient of the potential, giving us this final expression. Okay, so this is our u of t times the gradient of the gravitational potential. Now using, and basically we are done. Okay, so that's our final solution. Now let's transform this into the observation. Okay, let's transform this into something that is observable, which are the which are the spectrum. To do that, what do we see? How do we observe a structure that is forming? Okay, we have several of them that are forming across the universe, but let's pick up only one. And we have this gigantic object. Okay, we are in the linear regime, therefore we are on the 100 megaparsec scale or so, and the gravitational collapse is taking place. Therefore, our structure is starting to compress. Imagine that we are in this location and we are observing along this direction. Okay, so we are here and we are observing this object collapsing. So the density is getting higher and higher. What do we have? We have the expansion of the universe, so this object is going further away, therefore it's going to be redshifted in this way. But then we have this part that is a component of the velocity. So we have the peculiar velocity which is pointing in our direction, another one that is further, is pointing in the opposite direction. Therefore, this point is going to be more redshifted than the barycenter, which would be represent just the Hubble flow, the redshift given by the Hubble flow. So this would be the barycenter is basically our ZB, the velocity given by the Hubble flow. This one would be more redshifted, therefore it will look at a higher redshift with respect to its actual physical distance, whereas this other point here, it will going to be a little bit less redshifted, and therefore it look kind of closer to us, so we get this squashed. If we have the limit at which the Hubble flow is as a redshift which is equivalent by the incoming flow of the material here. So if the two are the same, they compensate each other. Okay, so we have that this part is going this direction with a certain compensated Hubble flow. This one is going to be speed up in the opposite direction, and so it would look like at a higher redshift, and in the end at this limit we are at this sort of collapse. It's like this spherical object in the redshift space looks like completely compressed. If we go to a further limit in which the velocity collapse, remember velocity are growing up, therefore the redshift of this point is much higher with respect to the redshift of the Hubble flow. Therefore what we are going to have is this sort of crossing, and the detection and this point that physically is closer to us with respect to the barycenter will actually be much more redshifted with respect to the background, and this point in the redshift space, okay, let's do, I don't know, like this, in the redshift space is going to look like on the back. Okay, it's going to be more redshifted, so it is going to look like, it gives you the impression to be on the back. And the opposite is true for this point. This point is going to give you a redshift here, and this one, as I said earlier, is going to be here. So you have this swap in the redshift space. The combination of all of these occurs at once because you're going to have on larger scales lower velocities, and in the core where the gradient of the potential is higher, you're going to have higher velocities, and therefore we are going to experience what is it here, this velocity in the center. You have a combination of all of that, so you're going to have large scales that look like squashed. You have a regime in which you have this sort of equilibrium, and then at even closer, or equality, better to say than equilibrium, there's no equilibrium involved here, but there are more, you have this limit in which you have equality between the Hubble flow and the incoming flow from one region and the other region. That gives you a sort of a narrow, very narrow place, and then you have the very core of the structure with high velocities that will look something like that. Okay, so that's everything at once, and indeed if you take your spectroscopic observation, that's what you see. You see the large scales giving you this slightly squashed ellipse. So you get then the regions in which you have the, you know, by the way, this is like a redshift is like that, and this is the parallel and orthogonal components. Then you have the regions with the squashing, and then you have the region with you have the squashing, and then you have the region with the you know, where you have the elongation along the line of sight. This would be the fingers of God. Okay, good. Let me just recap a little bit this point. So now we went for the velocity perturbations, so that in comoving coordinates that we call u. We use the very same hydrodynamical equations. We combine them together, so here you just have all the combinations of those equations, such to extract the information regarding the velocity that we assume to be modeled in this way. So we introduced a constraint that relates the velocities with the gradient of the gravitational potential. So this is an assumption but is well motivated. Using that, we just made the combination that I mentioned earlier. We introduced this function f that is defined like that, and this is coming from a fit. So this function that is arbitrary, but through the numerical solution that one can find, realizes the fact that actually is equal to this quantity. It's fully determined by omega n, by the amount of matter that we have across the universe. Having that, one gets the final expression for the velocity perturbations. last concept, you have how do you observe, that's the observations of these velocity dispersions, therefore that's observation through spectroscopy. You observe the velocities through spectroscopy, and you have the central region that goes with a certain Hubble flow, so that will be the redshift of this barycenter. On large scales you have low velocities that contributes at lowering the redshift of this portion and increasing the redshift of this portion, because these two, this redshift and this redshift, are working together, whereas this little redshift is suppressing this, the bulk flow of your structure, and this gives you this squashing in the redshift space. You have then, of course, the regime in which the Hubble flow is going to be equal to the infall flow for this direction, and then the infall flow for the other direction, and in the redshift space those locations look like collapsed in a line. And then in the core, where the velocities are higher because the potential is higher, you have that your Hubble flow might be this one, and then you have your infall flow that is larger with respect to the outfall flow. The same goes for this one, but in the other direction, and this gives you this sort of elongated feature in the spectroscopic space when you measure spectra. And take care that this portion that is closer to you is actually looking further away in redshift. This portion that is further with respect to yourself in the center of this barycenter, remember that we are watching along this direction, is actually looks closer, or give the appearance to be closer in redshift space, so it's less redshifted. That's called redshift space distortion, and when you put all these effects, large scales and small scales together, that's what you obtained.